Hello everyone. So this in this live stream we will be solving today's Leetcode problem, and the problem is count square submatrices with all ones. So I'm very much new to this problem. This is my first attempt, and we will be building the logic together. We will be understanding the problem and we'll be building the logic, and then check how it fits to the constraints. And if not, we will optimize it and try to make a successful submission. So yeah, let's get started, and I'll be just zooming this up. So yeah, so now we should read the problem statement, and the problem statement is about count square submatrices with all ones. So the problem statement is very short this time. Okay, so it says given m cross n matrices of zeros and ones. So basically whatever the matrix you have, so this will be a matrix, and in this matrix you have only 0 and 1 as its elements, right? You have to return how many square submatrices have all ones. How many square submatrices? So first you should understand what a submatrix is. So basically, if this is a matrix, like let's say it is not related to the problem statement, so I'm just using any random numbers. This would be something like this. So a submatrix is basically a particular part of this matrix, any part. Like you can choose either one element, you can choose either four elements. Basically you have to choose a few rows and few columns, and whatever the overlapping region is, it is a submatrix. So it is like if it this is the matrix, you can just grab any chunk from it. So this is like a submatrix. Okay, now what a square submatrix is. The square submatrix is the matrix which has if you grab this matrix, it is 1 2 0 0. So the number of rows in the submatrix and the number of columns in the submatrix. So the rows are this one row, two row. There are two rows and there are two columns. So if they are equal, then it is a square it is a square submatrix. Okay. So you have to basically tell. Let me just delete this. How many square submatrices have all ones? Okay. What does that mean? Have all ones? This means like if you grab some submatrix and you write it down, it has all ones, right? So very much a small problem in the context of problem size. Now you have to return the number. Basically, you have to return a number, like how many square matrices are there. Okay, let's go by the input examples. Basically, we have this matrix given to us, and you have to tell like how many square submatrices are there. So the answer comes out to be 15. Let's see how they have built it. So there are 10 squares of the side 1. So if you take a square of side 1 from this matrix, that simply means all the elements, right? So if you so a square of side 1 will be having only one element. So this is the like this is the set of all submatrices which has side equal to 1. Among these you count how many of them are all ones. So here we get 1 2 3 4 5 6 7 8 9 10. So here are 10 squares of side 1, which makes sense. Now there are 4 squares of side 2. So basically, if you now consider the side 2 thing, basically which is like this much, this particular square, and you have to slide it over. So by sliding I mean I'll just move it by one position, so it will capture this square. If I slide once more, it will capture this square, and then I slide down, it will capture this square. Then I slide this down, the middle one, it will capture this one, and the third one, if I slide one step down, it will capture this one. So in that, I'll just check which one of them are actually all ones. So let me just draw a bigger picture of it so that all of us can understand what I'm trying to build here. the logic, right? So just draw this particular matrix here. It is 1 1 1 1 and it is like 0 this part. Now what I'm saying, if you are looking for side 2, you just draw this particular window. This is the first starting window. I'll call this window 1, and now I slide this window to create other windows. So I slide this by one step, I'll be coming with this particular window. So I'll call this window number 2. Now I slide window number 2 to get this window, which will be our window 3, right? And these all windows are basically square submatrices of side 2. Now you just count how many of these. So now after that, what you have to do, now you have to pick each of these three matrices and expand them downwards. So I expand this one step down. I will come with 1 A. I'll call this 1A. I'll expand the second particular submatrix one step down. This will be 2A and this will be 3A. If we had more elements down below, it will be like 1B, then we will have 1C, similar to what we are following here, right? So now, so here you have already circled all the submatrices. Now you have to count how many of these are all ones. So I can clearly see that the matrix 2 has all ones, this particular reason, right? In fact, matrix 3 has also all ones, right? Now the matrix this matrix not, so this one is 0, so it's not a part of our answer. This has all ones, so it is part of our answer. So I'll just mark it like this, check mark will be there. And this is also a matrix which has all ones, so this will be also there. So how many check marks we have? 1 2 3 4. Now they have written here 4 squares of side 2. Now they have turned with the squares of side 3, right? So squares of side 3, if you come to that, basically that would mean this particular window, and you can just take it one step here. There are two windows, and here you see this window has all ones, so it will be like, it will be a potential count, and since there's no element below, so we cannot move downwards, so it will be like 1 square of side 3. Now we can move to side 4, which is possible in this case. And if we consider the matrix of side 4, in that case we will be having this part only. And if we try to expand it, so it's already the end, we cannot expand it anymore. So here we can see like it is giving us the, so it is giving us 0 for it's 0 squares for side 4, and after 4 you cannot really move ahead, so it's kind of a dead end. So it's like, yeah, we are kind of done with the exploration of example 1, and when we add it we get 15 as the answer. Similarly, we will test this logic in this particular matrix. Now let's build the approach. Let's write down the approach. How will you count them? How will you count them all? So the basic thing which we have done here, understanding the example, is a basic solution. And what is that solution? Let me write it down. So first thing first, just what did we do? So I'll call this algorithm. Okay. First thing first, we will start with square of side 1 and go till square of side min of rows and columns. So why I have written min of rows and columns? Let's say there are 3 columns and 5 rows. So in that case the matrix will look like this, right? In this case, if you try to construct a square, you can go maximum to the 3 sides. Basically, if you try to make a square, it will be of 3 sides. And if you try to make a square of side 4, this will fit in y direction, but it won't fit in x direction. So I hope you are very much clear to this. It's a very simple logic, right? And you can just take the min of these. So here it was 3. 3 was basically, let me draw this. So basically you cannot go beyond 3 in this case. Now let's say it had 3 rows and 2 columns. In that case we had something like this. So here you can go up to a square of side 2 only, like this. You cannot go till side 3, because if you expand this here, you need to expand here as well, which is not possible, right? So this is the first thing, like how many uh, basically squares, how many square side length we have to explore. Okay, so we have to start with square of side 1 and go till like this particular number. Okay, now the second step is to, for a side length, I'll call this x, right? So what we are doing here is basically the normal guy will do like this. It will uh, create all square submatrices. You can call it create, or basically lookup is also fine. Lookup into all square submatrices. Okay, and then you will be just counting the ones which are all ones, right? Counting the submatrices which are all ones. Okay, and you just append this count to answer. Answer is a global variable which will start with 0, right? So that is pretty much the simple thing, right? This is not a rocket science. Basically, we are doing a brute force approach where we are going to each square one by one and we are checking if it is all ones or not. Now, so this looks good and this is doable algorithmically, right? But now the next step which we have to do is to analyze its time complexity. Now the constraints part comes into play, which will shape our solution, which way we have to go. Otherwise, it's already solved here, right? But this solution, does it matches to these constraints or not? So that we have to now check. Now let's consider the time complexity. Uh, so the length of the particular rows and columns will be like, so basically the input will be given in Leetcode. It will be given like this. It will be a multi-dimensional array. So this is basically your number of rows, and this is your column. So it is of magnitude 300. So let's take it like 10 to the power 2. Okay. So how many square sides will be there? It would be 10 to the power 2. I'll call this particularly n. Right. So there are n square sides possible, and for each side, right? What are we doing? So we are kind of create creating looking into all square submatrices of that side, right? So how much complexity will it take? So let's say here, if we were doing it for size 2, so it was taking, like, you have to cover this horizontally, which will take you order n, right? That is very much the thing. And then when you expand downwards, it will take again order n. So it is order n square for traversal. We are not done yet. And then we also check then we also look into this particular these particular segments, right? And how much look that takes. Basically what we can do here is basically count how many times we have visited a particular node, a particular index, right? So if we are traversing, this will be visited only once or twice, right? This when we traverse down, when we traverse down, it will be like when we traverse down, it will be like again, it will be again two or something. So guys, there is some external noise. I'll try to lower the volume for some time. Yeah, I think now it's fine. My voice will be low, but yeah, due to external noise, I really have to do this. Okay. So pardon for any like I'll be turning it back in maybe 2 minutes. Okay. There is some band Baja Barat going on, and yeah, it will pass in maybe 30 seconds. I think you might be listening some noise or something. Okay, it's gone. Okay, okay, fine. So now we are moving back to this. So this was order in this side. This was order in this side. Now we are also checking each and every elements in each step, which is kind of I would say, yeah, is it order n square only or it is order n cube? Let me think. Think. The square of side 2, side 3, side 2, side 3. So this is basically 2 only, and when we explore down, it is like when we explore down. So the first when we travel it this way, it will be order order n for sure, and when we traverse down for each, it will be order n again. So it is okay. So it is like order n here, order n here. Okay, so this will be order n, and this will be order n. And how many? Okay, so it's obviously it's order n into order n because here you took order n steps, and for each you are doing this order n part. So it's like order n plus order n plus order n till n times in worst case. So it is n square only. So this lookup part is actually it's order n square, and this is also included in that. So here we are getting hmm. So here we are getting okay. So here we are getting n sides of squares, and for each sides we have order n square exploration. Yeah, it seems okay. Yeah, so it will be order n cube, and this will be basically 300 to the cube, which will give us 10 to the power 6 into 3 will be 27. So it is 2 into 10 to the power 2.7 into 10 to the power 7. Yeah, I think that is problem, I guess. The best case which passes in the given time limit is of the order 10 to the power 6, like something into like this. It should be like that, 10 to the power 6, broadly speaking, yeah. So this might fail, although I have heard it was 10 to the power 8. But yeah, the best solution is this only, and maybe I can check if what is the allowed time complexity in Leetcode. Let me just check it. I'm checking on my phone. So allowed time complexity, because we are on the edge here, and we need to really be sure like what solution will pass, right? Yeah, so I think we need to optimize this. We need to optimize this, guys. Uh, yeah, so okay, so someone is saying on lead code is it is 10 to the power 8. No, but the recommended thing is 10 to the power 6. But yeah, 10 to the power 7 may go in. 10 to the power 8 is also occasion in some case, but I have mostly heard it's 10 to the power 10 to the power 6 only. Mostly that. I'm not really sure. I just need to check. So are you guys aware of it? You can just write in the chat if you are there. Okay, I don't think occasion in some case, but I have mostly heard it. I don't think we have visitors here. Oh no way. So I'll just try to submit a solution of this particular complexity. If it fails, we try to optimize it further, or maybe when we are building the actual logic, we can come up with a better solution. Okay. So now how will we approach this quickly? Okay. So we will calculate the min of rows and columns with very much ease. So this is done. Second part is basically going inside it. So we will have a loop in from 1 to this number. I'll call this n. This is basically square of side I. So this is any ith step. We have to check for square of side I, and here we will have a window. Okay, so this particular window will be there, similar to this, right? It has a side I, and okay, how can we move with this? So there are two loops, right? So there is first movement is horizontal, and for each particular horizontal element there is a vertical movement, right? So what we will do, so this is I given to us, so we will declare a particular movement variable. So how we move here, so we are moving in x here. So guys, what will be our step? Let's say there are this many rows, this many columns, and we are at side 2. Okay, so what will be our movement step? It will be, so here we will use let's call this s here, right? Let's call this s, square of side s. S can be from 1 to n, so here it's s is 2, and now I'm calling iterator I along this side. So I will start from 0, and it will take a step like step rise of 2, basically step rise of s. So here the step rise will be plus s. What does that mean? So we are at 0 here. For the first iteration we are at 0, so we will be going from 0 till 0 1, basically two elements, because s was 2. And after that, when we are done with this particular index, we just increase I by the step of 2, so it will be changed to 2. Now we will be here, our starting point will be here, and yeah, so that is not the correct thing, right? I got it. So the step will be 1 only if you want to capture all the windows. So you have to move it by one index only. So step is anyway 1, right? And step is 1, and then you have to just inside that particular step here, the I plus will take a step of 1, so it will be at 1 here. Now we will go to one more element here, right? And then we do the check operation here in this particular window. We do the check operation here, and Okay, let me write it in a clean way so that everyone understands. Yeah, including me, guys. I also need to understand. Okay, so let me just do it. So this is the side of square. So we are starting with s equals to 2. So it's example case. So we will have two iterators, iterator I and iterator j. So iterator I will traverse towards x-axis, and this is our matrix, and we are with uh, window of side 2. So our I will start at 0. So this is 0, this is 1, this is 2, this is 3, and this is our j, which is basically 0, 1, 2, and 3. Now, so the first step is we start in the iterator of, so this is I and j initialization. We start with I. So if we are at I equals to 0, we are at I equals to 0, and then we will start with I equals to, so we are at j equals to 0. Okay, j is basically this. So j is 0 and I is 0, and then we will have j equals to 1, right? And then we have j equals to 2 likewise. So we are at j equals to 0, that means we are here, right? And I equals to 0 means we are at the first, j equals to 0 means we are at this particular level, and I equals to 0 means we are at this particular segment. Then I equals to 1 will be here, which will mean this particular segment. I equals to 2 will mean this particular segment. That will be the end, right? Likewise we will have some uh, so j equals to 1 means like we will be at here at this particular level, this particular level, and here I equals to 0, I equals to 1, I equals to 2, like that, right? So what we have to do in this case, so j is 0, I is 0, we will start with I 0. So these are the elements of the matrix we will take. So basically this is the j is basically the row number, and then we will take I, and then we just go in this direction for s steps, right? And then we will go in this direction for s steps, and you will just go in these directions. Whenever you encounter a 0, if 0, then you can skip this uh, particular step and you can move directly to this part, right? And then here also, if you spot any 0, you will just skip to this part. Likewise, similar things below this. Now one more thing is here. If you encounter let's see if it is, that will be a kind of optimization basically, but yeah, it is a very much good optimization, to be honest. But what I was thinking is basically, if we got, so if we got all ones here, so we'll obviously mark it to our solution, we'll increase our solution count. But yeah, if we encounter a good solution here, for the next step we won't be doing all this exploration again, like we won't be checking each and every element again. In that case, we will be just checking this particular column, and if it's all one, in that case you can just do a plus plus and move the same thing ahead. That will really save a lot of time. Basically, it will save the time in order of, okay, so here this particular traversal is not, is actually, yeah, it is a order of at the worst case it will go for, Yeah, basically, I'm not really sure about the complexity, how I'm calculating these areas. Let me just draw this. For example, if I'm going with this particular window, so we did 9 checks, right? If I move it here, we did 9 more checks, and likewise here also we did 9 more checks, right? So it will move in this manner. Like, let's say this is k, so we will have um, n minus k boxes, right? N minus k boxes times k square. This will be the complexity of each particular movement. So this is particularly n times k square, right? N minus k times k square. Okay. And if we go down here, it would be the same thing. Basically, it will multiply by n minus k again, because we will have n minus k movements down the hood. Right, so this is the entire complexity of each squared step, right? And you can say this is n minus k whole square multiplied with k square. And if you sum it over k equals to 0, k equals to basically 1 to n. Oh my god, this is a very much this is this is not n square. I'm really not sure about it. This is your if it is 5, then it would be like n is 10 and k is 5. It would be the maximum valued, I guess. Otherwise, no, it's like it is k times n minus k whole square. It is basically um, it is of type this, right? NCR type. And the time complexity will be the summation of it. What will be the magnitude? I think, yeah, it is. I guess it is safe to assume it is not. It is 10 to the power. Basically, it is n square only, or it is definitely not n to the power 4, right? Otherwise, we are doomed here only. So wait, this is basically the complexity of. There is a sigma here. So this is the entire complexity, man. This is the entire complexity of the algorithm which I'm currently writing, right? And we have to check if it is acceptable, right? And could go up to 300. In fact, k could also go up to 300. This can also go up to 300. So I have to check if it is. This also can go up to 300. Yeah. So this is really a summation of this part. hmm if it was just n square, so we would be getting n cube, right? If I kind of do integration stuff, like it is k square minus nk, it would go up to magnitude of 3. This will go up to, but yeah, there is a square here. um Pardon me, guys, pardon me. This is the thing. And This is really painful. Okay, so this is basically about time complexities. Let's build the solution and let lead code decide what is the if it is acceptable or not. So yeah, you got this logic, right? We will be moving like this, and we will be skipping it when we get 8 0 anywhere. Okay. Okay, that's fine. We can do some optimizations there, but um, if there is a possibility, then why not? Yeah, we can do optimizations if we have a TLE. Now let's go ahead and write the code only because the algorithm is this much only, not more than that. We need three variables, S, I, J, and we can just do it. So let me write code. And yeah, the major part of this problem which is difficult is about the time complexity and stuff. Otherwise, it's not that difficult to just like iterate like this and make it work. So first step first, we need to calculate the min of RC. So this is the matrix. So matrix is given in a vector format. What does that mean? Basically, these are your rows. So the rows length you can get it by calculating the size of the entire matrix, which you can do like this. So I will do integer r equals to matrix dot length. Okay, this will give the number of rows. So basically this is your rows, and then you have columns which will be matrix dot matrix. So for columns you need to check what is the size of each row. So all of them will have same size because it's a matrix, and that is for sure. Now you have to just check one more thing here, like can matrix could have like zero length. In that case, when you try to access the zeroth element, you will get runtime error. So for that, here we are sure because it is given here like the length is minimum 1. So we can access the zeroth index. Zeroth index is basically the first element. These are our columns. Okay. Now what we need to do, guys, basically we need to execute our logic. So what was our square max length? It will be min of rows and columns. We already talked about this. In case you forgot, basically minimum of rows or column will have the maximum square that can fit in the matrix, right? Now what we had to do, we had to iterate in this particular we have to iterate from square of size 1 to square of size n. For that, we'll just do this. For integer I equals to 0, I is, let's not take this I because we already had decided we will take that S. I and J are other iterators. Okay, so we will start with S equals to 1 and we will stop when S is less than, we will continue while S is less than equal to square max length. Square max length. And then what will we do here? We'll just iterate it by one step, and then we need to execute our core logic, right? So J is keeping track of rows, I is keeping track of columns. I is moving in this direction, J is moving in this direction. So we have to first take the bigger one, which is J. So we'll define our J over here. J is basically iterating alongside rows. So what will be the maximum value of that? It would be, yeah, it would be, yeah, but for the maximum value, you need to also consider the length of this square, right? So you have to check here. So if you add this much length to the square, So let's say the side of square is 1 and you are at j equals to 0. J equals to 0 means this particular row. So for side 1 square you can just go in this particular row. You don't need to consider the bottom row, right? For s equals to 1, for the square of side 1 you just need to consider one row, right? So in that case, what should be our stop condition? We'll just add s here, and we need to do a -1 here because we are using 0 indexing. So for j equals to 0, let's say we are here. So we are taking an example, right? So this is not the final. So how you do these things? For that you just need to take a simple case and that will extend it. So we are considering for j equals to 0 and s equals to 1. In that case, this loop should run one time, right? Because we will have to check each and every element inside it. So we should not, after that basically we will yeah, after that basically if we take this particular thing, wait, yeah, after that we will do a separate exploration of this particular level, then we do exploration of this particular level. But if it was 2, we should take this particular level, then we should take this particular level. In that case we cannot take this particular level. Okay, so that is where I want to stop. So if so I'll add the s thing over here to get the side square of side 1. So if j is 0, so if j is 0 here, and now if I add +1 to this, it will make j equals to 1. So that will take our program to like go till 2 loops for the particular thing, right? And that is not correct. Basically, you then need to do a -1 in order to stop yourself, uh, in order to avoid the index out of range error. Okay, so we did j plus s, and 0 plus 1 will take you to the square of okay, so guys, I have a better way to explain this. So we are at j equals to 0. This means like we are at this particular row. Now we need to check what is our side of the square. The side of the square is 1 in this case. If it was 2, we will go till here. If it was 3, we will go till here. If it was 4, we cannot go, right? So here we can go up to j equals to for a square of side 3, we can go up to j equals to 0, right? So for that, s is 3 and j is 0. So 0 plus 0 plus 3 is 3. I'm trying to find the hard limit. This should be less than the number of rows we have, right? And then I do j plus plus. So when I am at 1, I'll do 1 plus 3. 1 plus 3 is 4. 4 minus 1 is 3. So in that case, obviously I'll be stopping at 0 only. So for 0 it will pass like 0. 0 plus s, let's say s is 3. So 0 plus 3 minus 1 is 2. 2 is less than or equal to r. Then we will go with 0, right? And if it is not, then we will just stop. We'll just not continue this loop. Yeah. Now this is a particular this was a particular level, right? Inside that we have to form these submatrices and check, right? So here we need to go. So our starting point will be the particular j which was given to us and the particular I which we are currently processing. Okay, so what is the starting in x and what is the starting in y, right? So starting index in I is j. Starting index in sorry wait, starting j is this, and ending j is j plus s, right? Likewise, we have starting I is equal to I. Wait, we have not defined I here. So now we will obviously looping inside I. So we are now going inside I. So it will start from I equals to 0, and it will also go in a similar manner. But here it would be uh, columns, number of columns we have. So, and then we have these things here, starting I, ending j, starting j, ending j. Then we have starting I, and we have starting j, which was sorry, ending I, which will be I plus s. And now you just need to do this for you will iterate in rows and in columns. So this is for rows. So for I'll use two variables like let's say k and t. So this is for this part, sj, k is less than ej. So these are all absolute indices, so we don't need to care about the like out of range index here. And then we have k plus plus. Similarly, we do kt, right? Integer t equals to s of I, t is less than equal to s of j, and t plus plus is here. Here I do this. Now this is the main thing we have to check. If matrix of k and matrix of t is equal to 0, then in that case we need to say that then we need to stop our quest and we need to get out of this particular exploration, right? So we can break here, but we actually want to stop, right? So I'll just create a variable stop false, and here I just set stop to true, and here I just break. And we also need to break from this for loop. So if stop is true, then break from here. And again, if stop becomes true after this, then you can just break from this part as well. Sorry, you can just continue, not break here. And now we need to make sure if stop is false, we need to count this as a positive answer. That was it. That was it, the entire logic, guys, because we checked if we get a 0, we kind of break from here, setting stop to true. And if stop is true, we break from here. And now if stop is true, then we were anyway going to continue from here, right? So it is not needed. Then we got a valid answer if stop was there, right? If stop was false, then it means that we got a valid answer here. And oh, okay, so it was correct only. If we stopped somewhere, we are not incrementing our answer because we did not get a valid solution. So we just need to move to another step. Otherwise, we increment our answer. That is it. So this part is basically about uh, traversal in this section. Now, what I was afraid of basically it was the time complexity. Let's check this solution is correct or not. So it should first be correct, and then we worry about the time complexity. Okay. So what is the okay? So in C++ it's size. In JavaScript you use dot length. I was writing JavaScript code beforehand, so like JavaScript was in my mind. So guys, today I am actually kind of wasted. Basically, I have spent a lot of time in solving front-end challenges. So what is this error? Okay, so I guess it is due to reference, some incorrect reference. I'll just quickly check where do we get this error by making print statements. By making print statements, we could get the errors. Right, let's run this. Okay, so in the first one only we got this error. I think it's more related to this index accessing. So here we are starting with z equals to 0 all the way up to until when till j plus s minus 1 is equal less than equal to r. Okay, so let's examine the worst case. So s equals to s can go in this case s can go up to from 1 to 3, right? This is the 3 is the lowest one here. So it would be 0. So we'll start at this point and we'll do 0 plus 3 minus 1, 2. So 2 is pretty much less than equal to what? Okay, so this was the mistake. This is true, this is correct, but it should be this, man. Actually, okay, so this is true, number of rows, number of columns. But when you come to index based accessing, right, it is actually minus 1 over here. So you need to do minus 1 over here, or you can just remove that. It will serve the purpose. Okay, so we are getting some more errors. I don't think the error is here. Let's check where is the error. Can we print till here? Cout test and okay, so it is working fine. So where are we stuck? The error is saying reference binding to misaligned address for type int which requires 4 byte alignment. Note pointer points here. I really cannot get this error, to be honest. Still, how many? Okay, so for the first we did this. For the size one we did that, and so the good thing to would be to print i's and j's, right? Okay, so one more mistake I did here was this equal to sign. 0 plus 3 should be less than this. 0 plus 3 minus, yes, so now we are not getting such errors, but yeah, obviously we are not getting the answer as well. Let me just now debug this. For debugging purposes, we should actually expand this here. Okay, so now we are getting these answers. Okay, so we are getting answer as 5. Mm-hmm. Okay. I would like to see what was the answer for each step. Okay, so for answer of the first step was 4, which was correct. To be very honest, it was correct. For the answer of step 2, it was 5. Means it got incremented by only 1, which is not correct. Okay, for 1 it was 4, because so for 1 also it is not correct, man. For 1 it should come out to be 10, right? Freaking 10. So where are we getting stuck? Okay, so here we are starting with j equals to 0, and I'll just print cout j and cout answer. Then we can just debug this part. So j was 0 and we are at side 1. Then j was increased to 1, and then j was increased to again. um, yeah, so we have some issue here. Right, when we were at j equals to 0, we when we came to j equals to 1, it should be actually 4, and we are getting, so actually 3, we are getting 2. So it means we are kind of ignoring the last index. So for 0 it's like 0 and 0 plus 3, and the columns are like 4. So 0 plus 3 is 3, 3 is less than 4. So it will go from okay. It will go from 0, and when we increased it to 1, it was 1, I equals to 1. 1 plus 3 is 4. So it will not run, but it should actually run. When it should stop, it should stop when uh, okay, so it was like 1 plus 1, 2. 2 is still less than 4. Then we came to 3. 3 plus 1 is 4. I equals to 3. So I is 3, and 3 plus 1, we did 3 plus 1, which is 4. 3 plus 1 is 4, and 0, it was a 0. So I was 0, so I 0, and 0 plus 1 is 1. So we are considering 0 and 1. Okay, guys, so I think the problem is here. Um, First thing first, it should be EI, and we need to actually not go till here. We should actually stop beforehand. Same goes for this. So if j was 0 and we are at 1, so this will not go to the endpoint. So now we are getting some different kind of answer. We are getting 6. Okay, so we are getting 6 over here. Out of first loop we got 5. Now we got 5. Okay. So wait, let me just think about it. So we were at 0. We were at s equals to 1, and for s equals to 1 we will go by j equals to 0. Okay, so after 1 we stopped. Why did we stop? 1 plus 1 is 2, and I is starting from 0. Obviously it will go. Why did we stop? uh, why did not we? So it was 0, then it increased to 1. फिर उसके बाद it should be like 0 1, then we incremented it by 1 again, so it should be 2. So j was 2, so 2 plus 1 is 3, and r is 3 only. Okay, so it should be an equal to, because in this particular case you are under limits, right? And obviously that is a stop condition, to be honest. Yeah. Okay, so I really messed it up. Basically I should write it like this. So j ki, what would be the maximum value of j? It could go up to r minus s. So let's say if r is number of rows are 3, so rj for this, for the s equals to 1, rj could be 0 1 2, right? So j could be r, which is 3, minus s, 1 2. So j could go up to r minus s. Very much simple stuff, not a high stuff. Here also we need to think about this. What about I? If we are here, and what could be the, and we have a window of size 1, so what could be our maximum value of I which can go? So this is I equals to 0, I equals to 1, I equals to 2, I equals to 3. So we can go up to 3. So for s equals to 1, this should, the stopping condition should be like 4 minus 1, right? 4 minus 1. So it should be number of columns minus s, and equality will be holded over here. Then we are really much sure that yes, 3 is also there for let's say for let's say side equals to 1, r is c is 4 here, side equals to 1, 4 minus 1 is 3. I will go from all the way up to 0 to 3. And for I equals to, for s equals to 2, it will go up from 4 minus 2 is 2, it will go from 0 to 2. So basically it means this is your 0, this is your 1, and this is your 2. Now let's come to this adding part. So what will be the end index, right? So we just, obviously we, I think we are done at this place, right? This is very much true, because we have already covered this case earlier, right? And you see, this was the pain point. Writing this loop very much well. And let me just remove the print statements. Here we have this print statement as well, where we print the answer. And there is, I guess, one more print statement here. And now I run this and submit it. So this is again the worst approach only. We can make it better, but let's see if it passes or not. If it doesn't passes, then we need to obviously write a better solution. And guys, we are very much behind the time limit. Yes, so people have submitted solution which were like 11 ms, and ours is 239 ms. So it was clearly this case which I was very much concerned about from the start, this particular thing. So it was of the magnitude, this entire solution was of the magnitude 10 to the power 7, very much close to 10 to the power 8. So it is a worst solution. Now if we think to optimize it, obviously this is where the interesting part of the problem start. Earlier what we did was basically executed this brute force algorithm, nothing special. Okay, now it comes to optimize the approach, and let's see how we can use some of the uh, we can use some of the properties of these matrices to identify uh, any kind of pattern. Like let's say if we spot, so we store, wait a second. So let's say something like this exists. In this case, we are getting squares of side 1 only, right? We cannot form a square of side 2 because obviously it will require these elements as well. So how can we optimize it? So there will be n squares sides, and for each of them, if we kind of do this exploration in n square, okay, so it will be still n cube. So n square means like we need to touch each and every element once. So in the previous solution, we were doing worse than n square. Now if we just try to make a n square solution where we kind of just touch this particular square once, and then for the next part we consider this only. We don't need to compute here this particular part. For the next part we just need to consider this, and the data about this we kind of maintain, right? Oh, okay, so this is, I think we have, I think we can crack it. I think there is some good amount of, not amount, basically some good logic is coming in my mind. So let's see if we can do it or not. For this, let's take the simple case. For the this particular scenario where we have this, now let's consider this only, and we have a square of side 1. For this we have these two solutions only. So what I can do here is basically for this part is when I iterate, I keep track of how many number of ones I have spotted. Here I have spotted 0, and if I come here, I just want the number of zeros before this in my area. So basically, if we are considering square of side 1, we don't need to ask like what was the this part previously, right? So let's say we counted, it was 0. Now we are here for this particular index, it is independent, so it's again 0. Here also we didn't need, so it's 0. It's basically 1, and we counted it. Now when we go to square of side 2, it becomes interesting. Let me just show you. If we had this kind of information, so first we will start with this kind of square. So then what we keep track is basically we keep track of consecutive, basically for each column we keep track of, again that will be expanded on columns. Okay, so we keep track of how many rows have all ones. If we're moving downwards, then in that case it would be a separate computation. Okay, now so here also we need to do this. Here we need to keep track how many of these are already ones. Yes, how many of these are. Here we need to check this part. Here we need to check this part, this part, this part. All right. Let me think. Can we build it? If I do this, let's say there was one here, and if I make a prefix sum, it would be one, two, three. So when I'm at this point, I will just do for this part. I'll just do so here. I'll just do 3 minus 1, which is 2. So here I got 2, and here I got 2, and here I got 2. So I will get some strips which are consecutive, right? So here the count was 2, here the count was 2, here the count was 2. So it will form a rectangle which has 2 as a side length, and then we just need to check how many square of side 2 we can grab, which is basically this n minus k. Hmm. I think I have cracked the logic. Let me just go ahead and explain it to you all. So what I have done here is this. So basically, what I'll just draw any random. Why random? Let's just consider this particular case only. Here, yeah, it was a 4 cross 3 matrix. I can just draw that kind of matrix, and let me use some different color this time. Okay, so this is 4 cross 3, right? Perfect. I just write the values. It was okay, you guys are not seeing it. Yeah, so now it is basically 0. I'll just write the element in the matrix. It was okay, first and third are same. Okay, so it was this. Okay, it was 1 1 1 1. Now, so the idea which I came up with was this. I'll keep prefix sum count in columns. So here it is 0, here it is 1, and here it is 1. Here it is 1, here it is 2, here it is 3. And here it is 1 2 3, 1 2 3. This is prefix count in this direction, right? Makes sense. Now for the first case, we will be considering squares of this particular row. So here, um, these are the squares of side 1. So for s equals to 1, okay, we will just iterate in this manner. So we check which square has value 1, or we check the prefix some difference. So it is 1 for here, so we'll simply calculate for this. It will come out as 10. Now for s equals to 2, let me just undo what I did for s equals to 1. Now for s equals to 2, we will start from here. Make sense? We are focused at the bottom point, right? This point. Cool. What we will do, we will grab this. So we will basically take the entire section here, and we'll take the entire section here, and we'll grab the bottom ones. So what we did do here, basically calculate for each particular row. We write down the sum of ones in the particular segment here. How many ones are there? So it would be basically prefix value of this minus prefix value of here. So it's none of like rows is here, so it's 0. So it will be the end value here. So we just quickly write down that 1 2 2 2. If it was not this particular segment, we could have subtracted the row above this to each of these values. So it was 1 2 2 2 2 2. So and you are considering square of side 2. So you just check how many of them are consecutive. So you see here it's 3. So it means that there are 3 consecutive rows which have all ones. And how many square of side 2 you can create out of this? So bro, you can create out of this you can create basically 2 such squares, which is nothing but n, which is 3, minus s, which is 2 plus 1. 3 minus 2 plus 1, which is 1 plus 1 equals to 2. If you spot such kind of contiguous thing, right? Yeah, so how will it help you to reduce the TC? So in that case, we don't need to iterate each and every element. We just iterate order n times for each particular rows. So there are n rows and order n time. So this will be order n square for sure, and then we have s square sides, which will go up to order n only, and this entire thing will be again n cube. It will be n cube. Can we do it in n square? If we want to do it in n square, then we should take order 1 for each step. And how we can take order 1? Can we? So guys, this is also order n cube solution, and I'm not really sure if it is better than this because it is also n cube only. I'll just check what people have submitted. I really I really don't want to check, but obviously we need to check. If we're looking for the better solution, has anyone mentioned time complexity? This is order 1 space. Oh, this is order m in time. Basically, it's order n square approach. They're using dp. Okay. I won't open any solution to be honest, because that really hinders the thinking. Yeah, so I think this is scan the matrix to identify squares and count them. So yeah, people are using DP. Okay. Recursive approach is basically which we are doing here. It's brute force solution. And um, I think, yeah, so the editorial also says you have to use DP. And DP is a different thing. Now I know if I can solve it with DP. It's not that thing, man. It should be like, it should come on its own, right? Then there is bottom up approach. It's DP only. And then we have the complexity analysis. Okay. So I don't think we can, by a greedy way, we can do this in a better than order n cube solution. So I think this was a greedy approach only, and even if we implement this particular greedy solution, it will also take order n cube. So that is why I'm not implementing it. Now since I know so guys, to be very honest, this did not come to my mind that we can use DP in this solution. Now that I know if we can use DP here, let me think how we can make it better, how we can move it that way. So DP is basically about caching, and caching is basically about identifying, basically dividing the problem into smaller sub problems which are of the same structure, and you can just simply cache the results to build the entire solution. So if I talk about the DP solution, it should be let's say if we got For this particular submatrix, if we got the solution as like if we got 10 such squares, right? Okay. And yeah, so we have 10 such squares. Some exist there, some exist there. And now if we try to include this, include this, how can we implement DP here? Wait, let me think the commonality. Let's say if we have this matrix which was 0 1 1 0, and will if I will add if I want to add some more, uh, uh, I want to extend this space. In that case, in order to make squares, it should be, yeah, you have to find a particular link, then only you can solve things, man. How can we do that? Oops. Let me think, yeah. This is 0 1 1 0. If it was 0 1 1 0, in that case, if I get 1 1 here, we are forming these regions. To be honest, I'm really blank at this, and probably I will check the solution. And if you guys need me to explain that solution, then you can just comment down below. And guys, maybe I'm very much exhausted. As I told you earlier, I have done a lot of work today in some mobile app development. So currently, it's very much hectic for me to continue this. So yeah, we have the solution that passes the constraints, but yeah, we don't have better solution today. But yeah, I will posting a video of better solution and on this channel so that we can all learn from that and understand how they solved it. Understand, we'll learn some paradigm to apply it in other problems. Okay, so that is it for today, guys, and we'll meet tomorrow for sure.